In this module, we are going to now start the derivation for the Nusselt number for a constant wall heat flux boundary condition. So, the main agenda of this in the next module is derivation of Nusselt number for constant wall heat flux case for flow through a circular pipe. So, you have a flow through a circular pipe, laminar flow, circular pipe. We want to show that Nusselt number is equal to 4.36, which is a constant. This is what at the end of this module, or probably half of the next module, we are going to prove. So, if there is a pipe of diameter d and heat flux is equal to constant, then we have seen that wall temperature as well as the bulk fluid temperature are going to vary like this, and in the fully developed part, in this part, this is fully developed part, delta T is constant. That means, even though the bulk fluid temperature is varying and the wall temperature is varying, you are going to have the driving temperature difference is virtually constant throughout. Okay. And we are defining the heat transfer coefficient as Q double prime is equal to H into T wall minus T bulk mean, or Nusselt number is defined as H d by K, A of the fluid. H is nothing but this one. This is my definition of Nusselt number. Okay. So, if I have a circular pipe, and for this we are going to start off with determining the steps involved are to study the velocity distribution. This has been done in fluid mechanics, but most students would have forgotten this. So, we will have to redo this for the students. Velocity distribution or velocity profile for laminar flow through a circular pipe. U of r we need to find, and we all know what it is going to look like. Say it is going to appear to be a fully developed laminar velocity profile in a pipe would be a paraboloid of revolution. So, this is u of r. This is u of r. Okay. So, we are going to derive the expression for u of r. So, step 1, get the definition of u of r. From this, get the average or mean velocity, get the expression for maximum velocity or the center line velocity, and then go to the energy equation. So, this is from the momentum equation, then go to the energy equation, get T of r from energy equation. Remember, when we go to the energy equation, we have the velocity distribution which is going to be fed in. So, there is a strong coupling between this information into the energy equation and then the resulting temperature profile. From the temperature distribution, you get the T bulk mean. From this, you get your Nusselt number. Okay. So, this is the logical path which we are going to take. Okay. So, let us start with the continuity and the momentum equation for flow through a circular pipe. Remember, this is going to be in polar coordinates or cylindrical coordinates. So, cylindrical coordinates r, theta, z. I use z instead of x because it is a little bit more convenient, and the continuity equation in cylindrical coordinates has been simplified. We can simplify the continuity equation. It is written this way. So, continuity equation is going to be given by 1 by r d by dr of r u r plus 1 by r d by d theta of u theta plus du by dz equal to 0. This is my continuity equation, and my 3 momentum equation, Navier-Stokes equation in cylindrical coordinates are already given here, axial, r and theta. Okay. So that I do not have to spend time writing this. This can be obtained from any standard fluid mechanics textbook. I have merely copied these so that we save some time. We are going to simplify this. Okay. So, before we formally start the derivation, what are the assumptions that are going to be made? So, we have a list of assumptions we need to say very clearly. So, what are the assumptions? And this is very important in deciding the nature of the solution. First assumption, steady state, which means d by dt of any quantity with respect to time is 0. This is steady state. Second, the axial direction is infinitely long. So, we do not have any specific favor with any particular x or z location. We are talking of fully developed flow. This will be a result. So, let us not put this as an assumption. We are going to get this as a result, not an assumption. Please do not. We will get this as a result. Okay, make a note of this. So, I won't call this number 2. Number 2 is pipe very long in z direction. That means there is no specific favor with a particular z location. Parallel flow, laminar flow, essentially where the streamlines are this way. So, u of r is equal to 0. So, you do not have any velocity in this direction, this is not there. So, parallel flow u of r is equal to 0, incompressible flow, Newtonian fluid and constant properties. Of course, laminar flow. 6. Axisymmetric flow. Oh, sorry, 6 we can write dP by dz is equal to constant. That means pressure varies linearly along the flow direction. Number 7, axisymmetric. That means the flow is not partial to any specific theta, no swirl component. Therefore, u theta is equal to 0 and d by d theta of anything equal to 0. Axisymmetric means d by d theta of anything equal to 0, no swirl. So, it is not like a vortex which is being generated, what you see in a when you open the drain of a wash basin, there is a swirl component. So, we do not have any such swirl. The flow is perfectly laminar, no swirl, no rotational component, etc. Gravity effects are negligible in all directions. So, gravity effects neglected. When we say neglected, it means it is very small compared to the other forces which are there, which is the inertial force, pressure force and the viscous forces. Okay. So, with these assumptions, and I have already written only the steady state continuity equation. So, this d 1 by r d by dr of r u r. So, if this is the pipe, you are at some random location. So, this is the inlet, this is somewhere going further straight, your boundary layers have merged, you do not have any component u r, you are somewhere in this part of the flow. Steady state, we have already dropped off the term, u r is equal to 0, we have told from assumption 3. So, this term is going to go to 0. u theta is 0 or d by d theta of any quantity is 0, which is from assumption 7, and this gives me my continuity equation du by dz equal to 0. I am purposely dropping off the subscript z, du z by dz actually it is, but since we do not have any other component of the velocity, just for simplicity we are replacing uz by simple u, no other reason. It is the axial component of the velocity is what is represented by u, and continuity equation tells me a very important thing, saying du by dz is equal to 0. What does that physically mean? So, this is slide number 9. Du by dz equal to 0, it means that u is a function of r and theta, because gradient with respect to z is 0. So, u is at best a function of r and theta, but we said nothing is a function of theta. This was an assumption, and this is a quite a realistic assumption. That means u is a function of r only, and this is what is called as a fully developed flow. In fluid mechanics, we have seen this term fully developed flow. That means if I have this, please mathematically I think all students would be able to understand or tell us the condition for fully developed flow, but physically what it means is that if I have a profile at z1 and I want to check the velocity profile at z2, it is exactly the same. So, if I take this picture velocity at z1 and superimpose with the velocity profile at z2, it is identical, both qualitatively and quantitatively. That means velocity at every point is the same, the curve shape is the same. So, identical qualitatively, that is in shape, and quantitatively, that is in values also. So, this is called as fully developed flow. We already had said u is not a function of time, therefore, we are left with u is a function of r only. That means d by dr of u is nothing but d by dr of u. What does this mean? Variation of the axial component of velocity in the radial direction is no longer a partial derivative, but a regular derivative. Now, we go to the Navier-Stokes equation, which I have already written so that we save some time, and we are going to strike off terms based on assumptions so that we get a simplified form of the Navier-Stokes equation. So, let us look at the axial momentum equation first. Axial momentum equation is written here, that is in the z direction it is steady state. So, this is the first assumption, steady state. Number 3, parallel flow. So, ur is 0, therefore, this term goes to 0. Anything with respect to theta is 0. So, this term because of assumption 7 goes to 0. Du by dz was shown to be equal to 0 from continuity equation. This was the condition of fully developed flow. So, this is 0 from continuity equation. We just showed it a couple of minutes ago, fully developed flow. So, this is 0. dp by dz retains here. This is gravity is neglected in all directions. So, this is assumption 8, and assumption 7 is this, because gradient with respect to theta is 0. If du by dz is 0, that means u is not a function of z, the second derivative is also not a function of z. So, I can just put u is a function of r only as the reason. This was a result of the continuity equation. So, my axial momentum equation is now simplified. I am going to take a fresh slide here to write this. Axial momentum equation from here is pressure term and viscous term is there. So, we will write this. So, So, the z momentum equation simplifies to the following: mu by r d by dr r du by dr is equal to, there was a minus sign there, when you bring it to the other side it becomes plus dp by dz. Then next we are going to look at the r momentum equation. R momentum equation, again you have steady state, this is assumption 1, u r is 0, no it is a parallel flow problem. So, this is 0, u theta was 0, number 7. So, this also goes to 0, same reason for this. There is no radial component of the velocity. So, this also goes to 0, gravity is not there, this is all going to be 0. Assumption number 3, u r is equal to 0. So, all these terms are dropping off because of assumption number 3. Okay. And this one assumption number 7, and this is also assumption number 3. R momentum equation was simplified to dp by dr equal to 0, and theta momentum equation was identically 0 equal to 0. Now, I take a look at the theta momentum equation. The theta momentum equation is now going to get simplified. U theta is 0. So, every term, this is steady state, we do not need to go into term by term. Assumption 7, everywhere either u theta is 0 or d by d theta of any quantity is 0. So, everything wherever u theta is, those terms drop off, wherever there is a derivative with respect to theta, those terms drop off. So, ultimately you get 0 equal to 0. I am not going to spend time cancelling term by term, every term is identically equal to 0, even the pressure term is going to drop off. What does this tell me? dp by dr equal to 0 implies p is a function of z only, because p is not a function of r, time and theta. Nothing is a function of theta, p is not a function of r, we had assumed steady state. So, p is a function of z only. As a result, dp by dz becomes a regular derivative, the first thing. Now, z momentum equation we had also shown before that du by dr became equal to regular derivative, the partials were lost, we went back to the regular derivative here, and therefore, we can write mu by r d by dr of r du by dr is equal to dp by dz. So, this is your simplified z momentum equation, because we had shown u is a function of r only, u not a function of z, not a function of theta, not a function of time. Continuity equation gave me this, right. So, now our job is to integrate this. So, 1 by r d by dr of r du by dr is equal to 1 by mu dp by dz, okay, which means d by dr of r du by dr is equal to 1 by mu dp by dz into r. So, first integration gives me r du by dr is equal to 1 by mu. Remember, dp by dz was told to be constant, it is not a function of r anyway. So, this comes out and you are left with r square by 2 plus C 1, which can be written as du by r is equal to 1 over 2 mu dp by dz r, divide through by r. So, this r comes out here and cancels with 1 r, and you are left with C 1 by r. This is your first derivative. Remember, we will end up using this form not this form for using the boundary conditions. We will see that in a minute. So, then we go and integrate the second time. So, integrating again I get u of r is equal to 1 by 2 mu dp by dz as it is. R integral is r squared by 2 plus C 1 log r plus C 2, C 1 log r plus C 2. So, which is written now in a nice way as r squared by 4 mu dp by dz plus C 1 log r plus C 2. This is my velocity distribution. Two unknowns C 1 and C 2 constants, I need two boundary conditions. These two boundary conditions are, first one, at r equal to 0, du by dr equal to 0, which is the symmetry boundary condition or maximization of the velocity at the center line. Second boundary condition is at r equal to capital R, u is equal to 0, which is your no slip boundary condition. So, I substitute boundary condition number 1. If I substitute boundary condition number 1, I said we are going to use it in this form, du by dr equal to 0 at r equal to 0. So, left hand side is 0, this is also 0, it gives me C 1 is equal to 0. Therefore, r equal to 0 and du by dr at r equal to 0 equal to 0. This gives me C 1 equal to 0, very nice. Second boundary condition is r equal to capital R, u of r is 0, I get 0 is equal to u of capital R, which means substitute here 0 equal to r squared by 4 mu dp by dz plus C 1 log r is 0 plus C 2 gives me C 2 is equal to minus r squared by 4 mu dp by dz, capital R squared by 4 mu dp by dz. Therefore, u of r, the expression for the velocity I substitute here is r squared by 4 mu dp by dz minus capital R squared by 4 mu dp by dz. I simplify this into a form which I like, minus r squared by 4 mu dp by dz comes out, bracket I get 1 minus r by r whole square, which is your velocity profile or velocity distribution. Notice that this has a minus sign in front, dp by dz has to be negative in the flow direction always. Therefore, this term is negative, there is a minus sign here, velocity will come out to be positive because the square bracket is always less than 1 between 0 and 1. Maximum velocity is at r equal to 0, u is equal to u max or u center line, which is nothing but minus r squared by 4 mu dp by dz. So, this is one important quantity, center line or maximum velocity minus capital R squared by 4 mu dp by dz. My next step is to get my maximum velocity. I can write it here itself. U max is when r equal to 0. So, if I substitute r equal to 0, u of 0 is u max, center line velocity, which is nothing but put r equal to 0, you get minus r squared by 4 mu dp by dz. This is the velocity or maximum velocity. Note that dp by dz is always negative, pressure decreases in the flow direction, note this. So, this keep in mind, therefore, this term is always positive because r squared by 4 mu has a minus sign in front of it. This bracket is always positive, dp by dz is always negative, u of r is always positive. Now, we are left with getting the average or mean velocity. U mean is equal to integration 2 by r squared u of r dr. Where does this come from? This comes from mass conservation rho u bulk mean A cross section is equal to rho u r dA, integral over the area. Cancel the rho because incompressible, and for a circular pipe AC is equal to pi r squared and dA is equal to 2 pi r dr. So, when I put this and segregate the terms, you get u m bar is equal to 2 pi by pi r squared integral over the area r, this r remains u of r dr, that is what it is. Okay. So, I substitute for the profile 2 by r square integral 0 to r minus r squared by 4 mu dp by dz as it is r 1 minus r squared by capital R squared dr, which is nothing but minus 1 by 2 mu dp by dz. Capital R's cancel off, 2 and 4 cancels off, and you are left with integration of this r minus r cube by capital R squared dr, which is nothing but minus 1 by 2 mu dp by dz. This is integral, this is nothing but integral r squared by 2 minus r to the power 4 by 4 as it is 0 to capital R, which is minus 1 by 2 mu dp by dz r squared by 2 minus r to the power 4 by r squared would be r squared by 4, and therefore, u bulk mean is minus 1 by 8 mu dp by dz. U maximum was minus r squared by 4 mu dp by dz. Therefore, u max by u bulk mean is minus 1 by 4 mu dp by dz and divided by minus r squared by 8 mu dp by dz gives me u max is equal to 2 times u bulk mean velocity for a pipe. Okay. So, we stop with this, and in the next module we will continue with the simplification of the energy equation, use the velocity profile and the equation for u bulk mean in the energy equation, and then go ahead and derive the temperature profile, calculate the bulk mean temperature, and then define the Nusselt number. Thank you.